Assalamualaikum and hi! Good day to all panel and to everyone who watched this video. I am Nurul Hanisah binti ABDUL, a final year student of Bachelor of Science with Honour Polymer Technology student of UITM Perlis. My supervisor is Dr. FAIEZAH binti HASHIM. Today, I will be presenting my final year project entitled NANO-CELLULOSE for Active Food Packaging. This slide presentation consists of introduction, literature review, conclusion, and recommendation. So let's get right into it. Consumer demand for a range of foods throughout the year, as well as a preference for convenience, has led to a massive surge in innovative food packaging inventions to ensure the availability of safer and healthier foods. Food packaging is essential for maintaining food quality and safety while also extending the shelf life during storage and transportation by protecting them from physical, environment, chemical, and microbiological dangers. Microbial food decay primarily focuses on the surface of the food, so food packaging helps prevent this from happening. Since the middle of 20th century, plastic produced from petroleum have been the most common material used for food packaging. However, due to inappropriate disposal and non-biodegradability, more than 30% of the plastic was end up in landfill. As a result, consumers want environmentally friendly, safe, and non-toxic product. So, biopolymers have gained a lot of interest because of their biodegradability. The most popular active packaging methods are those that release antimicrobial chemicals onto the food surface, reducing or slowing microbial development and food degradation. Over the last decade, research in the field of nanotechnology has exploded. Due to that, cellulose, as one of the most abundant renewable substance produced from the ecosystem, was chosen in this review. NANO-CELLULOSE can synergistically collaborate with other materials to improve the nanocomposites barrier, thermochemical, and rheological characteristics. NANO-CELLULOSE is a widely used material for active and intelligent packaging because of its antibacterial and antioxidant capabilities. One of the problem statements is there has been an increase in demand for packaging materials which are biodegradable, pose very minimal threat to environment, and manufactured from sustainable and renewable resources. The community is also especially concerned about the environmental consequence of excessive plastic use, and they are looking for alternative bio-based material for food packaging. And last but not least, nanocellulose has the potential to be an excellent antibacterial substance against microbes. This material is widely recognized for its excellent properties, which include a high specific surface area, biodegradable and renewable, and having a high mechanical strength. Due to their exceptional mechanical characteristics, nanocellulose is anticipated to be a great reinforcing agent. Additionally, it has a high gas permeability and might lessen a film's water vapor permeability. The creation of nanocomposites film in the presence of nanocellulose technology is anticipated to increase food quality, increase shelf life, and act as active material carriers for antioxidant and antimicrobial substance. The primary focus of this review is to provide an overview of those nanocellulose materials in active food packaging application. Cellulosic packaging primary goal is to enhance and encourage economic health. Specific emphasis is given to antimicrobial and antioxidant packaging systems. Furthermore, the characterization, mechanical properties, and antimicrobial activity of nanocellulose material, as well as morphological analysis, are discussed in depth. Next, we move on to the overview of nanocellulose. Nanocellulose may be extracted from plants or synthesized by microbial fermentation. It has exhibit great potential to enhance bio-based materials due to its availability, renewability and degradability, and physical, chemical, and morphological qualities. Two main types of cellulose nanostructure may be obtained, which is cellulose nanocrystals and nanofibrils. CNCs can be synthesized from natural fiber using acid hydrolysis, yielding extremely crystalline and hard nanoparticles that are shorter than nanofibrils synthesized via homogenization or grinding. CNCs can help to develop nutritious, sustainable, and safe food and beverage that meet ever-increasing customer demands. CNCs also have strong mechanical properties and high surface area. Moving on to cellulose nanofibrils. CNF can isolate it from plant cell wall. Chemically, cellulose fiber are made up of a linear chain of hundreds to thousands of diglucose molecules. CNF have demonstrated great transparency, outstanding mechanical characteristics, and strong biocompatibility as research has evolved. They have increasingly found their way into antibacterial packaging, gels, and composite materials. Moving on to the characterization chapter, one of the most important testing is Fourier transform infrared spectroscopy testing. FTIR is widely employed to characterize and quantify the study of polymer blends, as well as the identification of their compatibility via intermolecular hydrogen bonding and the investigation of their degradation process. Brady and Rim made characterization of bio-nanocomposite films prepared with agar and paper mulberry pulp nanocellulose. Crystallized nanocellulose was separated from paper mulberry bus pulp by sulfuric acid hydrolysis method, and they were blended with agar to prepare bio-nanocomposite films. The results of FTIR show that there was no distinctive change in absorption peak positions of the CNC compared with those of the mulberry fiber, which indicates that the acid hydrolysis of mulberry fiber did not affect the chemical structure of cellulose fragments. Based on the results, the crystallized nanocellulose obtained from the paper mulberry bus pulp can be used as reinforcing agent for the preparation of bio-nanocomposites, and they have a high potential for the development of completely biodegradable food packaging materials. The next testing is scanning electron microscopy analysis. SEM is a test method that uses an electron beam to scan a sample and provide a magnified picture for examination. Microanalysis and failure analysis of solid inorganic materials can both benefit from SEM analysis. A study by Young showed the synergistic effect of cellulose and lignin nanostructure in the A-base system for food antibacterial packaging. The surface morphology of samples shattered in liquid nitrogen and gold spattered was used to investigate the microstructure of PLA and PLA nanocomposite film. FACM micrograph of neat PLA and PLA nanocomposite fracture surface are shown in the picture. In both clean PLA, a smooth fracture surface was visible, indicating strong interface addition between the LNP and PLA matrix. So there were no microdomains and the surface was homogeneous due to the good dispersion of LNP nanofillers in the PLA matrix during process. Verifying the mechanical performance of nanocomposites, including lignin nanoparticles at the specified weight amounts. The next important testing is tensile. The tensile strength of a material is used to calculate the maximum force that a material can withstand before it ruptures. It determines the maximum load-bearing capacity of the material. A study by Young showed the synergic effect of cellulose and lignin nanostructures in polylactic acid, base system for food antibacterial packaging. It shows that all the nanocomposites had greater tensile strength and Young modulus compared to pure PLA. This is because ternary system nanocomposites had better strength and modulus than plain PLA and binary system nanocomposites. Antimicrobial packaging system is a novel development which incorporates antimicrobial agent into a polymer film to suppress the activities of targeted microorganisms that are contaminating foods. So this is one of the most critical features of food packaging safety, as it is impact on the food microbiological shelf life. Referring to Hassanin and Mustafa, who investigated tempo-oxidized cellulose extracted from bagasse as potential antibacterial biocompatible agents, found out that the PHE-TOC demonstrated potent antibacterial action against a diverse microbial population, the majority of which were infectious strain. Furthermore, the TOC demonstrated outstanding performance in terms of rapid microbial population as well as low MIC values. They used 3 different methods to evaluate antimicrobial activity: agar plate diffusion, statistical analysis of MIC data, and time required for killing. As a result, it was expected that the compound can act as antimicrobial agents. Last but not least is antioxidant testing. Antioxidants are free radical scavengers that help to delay or prevent oxidation. Antioxidants, in fact, lower the capacity of active antioxidants in the food system, hence limiting the amount of oxygen in the food system. One of the findings from Roy and Rahim showed that adding curcumin and zinc oxide affected the physical and functional properties composite, where it demonstrated excellent antioxidant activity as well as strong antibacterial activity against foodborne pathogenic bacteria. Zhang also discovers cellulose nanocrystal and cellulose nanofibril as outstanding control release agents and stabilizer, boosted the antioxidant and antibacterial characteristic of edible food packaging films greatly. In conclusion, a natural polymer called nanocellulose, especially cellulose nanocrystal and cellulose nanofibrils, has huge potential for usage in the food business as ingredient or as unique packaging. In addition, for being biodegradable, accessible, and sustainable, nanocellulose made from renewable resources is also reprocessable and recyclable. Applications of nanotechnology will open up new markets, resulting in new goods and income. As recommendation, some approach for improving the properties and performance of antimicrobial packaging material, such as polymeric blending, chemical and physical modifications, have shown promise for a variety of application. Researchers have been attempting to produce biodegradable films in the last couple of years using entirely green ways that do not involve the use of any chemical reducing agent in the process, such as plant extract, UV reduction method, and etc. Material scientists and engineers should collaborate in order to utilize nanocellulose in commercial packaging. The general use of such a sustainable and biodegradable nanocellulose in place of its plastic equivalent would undoubtedly aid in the reduction of greenhouse pollutants. And that's all from my presentation. Thank you.